In this section, we're going to look closer at molality, which is the little m, which is not something I've used a lot in practice, but it's extremely helpful for talking about colligative properties, which is what we'll get to soon. So next, let's look at molality, which we will only use for this chapter. We tend to use molality to look at colligative effects on solvents. We will get to what that means in a few minutes. For now, let's do the calculations. Molality is moles per kilogram. Again, in water, liters and kilograms should be the same, although it's worth mentioning that molarity is liter of solution, whereas this is kilograms of solvent only. As the concentration goes up, the volume of those solutions is going to be different than the kilograms of solvent, or farther and farther apart anyway. So anyway, the extra thing we have to do here is we have to figure out how much weight the solvent has. Okay, so we are also, for this argument, looking at a different solvent other than water. So what is the molality if 7.3 grams of NaCl are added to 450 milliliters of ethanol? So first things first, we do have to find the moles of solute, which is the NaCl, the smaller amount. Again, from the periodic table, I find that NaCl is 58.5 grams for every mole. So 7.3 grams divided by 58.5 grams per mole gives us 0.125 moles of NaCl. So we have the density of ethanol is 0.789 grams per milliliter, and 0.789 grams per milliliter equals grams over 450 milliliters. If you do the math and cross multiply 450 times 0.789, you get 55 grams, which would be 0.355 kilograms. So now we take our moles of NaCl over the kilograms, and we find this is 0.352 little m NaCl, and then because it's not water, we're going to write in ethanol. So try this one really quickly. Determine the molality of KBr when 15.2 grams of KBr, 119 grams per mole, is dissolved in 350 milliliters of ethanol. Ethanol has a density of 0.789 grams per milliliter. So go through that. When you're ready for the answer, press play, and we'll go to the next slide. Okay, so the moles here are the same as before. We've got 15.2 grams of KBr, 119 grams for every mole, grams and grams cross out, and we're left with 0.128 moles of KBr. For density, we have to use the density equation. We have the density, we have the volume. We're going to cross multiply on both sides, and that should give us 276 grams. So our molality is just the moles over the kilograms, so I'm getting 0.464 molality KBr in ethanol. With all solutions, we need to know exactly how many moles of chemical are in that solution. For one, if it's a chemical reaction, we need to know how many actual reactants will react, and therefore how many products will form. In this case, we're trying to make a specific concentration of solution, so we need to know how many moles of chemical to start with to make the solution correctly. In this case, we have a 1.5 molal solution and 0.130 kilograms of water. Now, just like molarity, we can use molality as a conversion factor. It would be 1.5 moles of NH3 per 1 kilogram of solvent. But I usually find it easier just to set this up as a mathematical equation. We're going to plug in our molality, we're going to plug in our mass of solvent, and we are going to solve for moles of solute. So we do that by cross multiplying. Multiply both sides of the equation by 0.13 kilograms, and that will cross it out on the right-hand side, and we're left with 1.5 molal times 0.13 kilograms equals moles. Note, it's usually easier to change these combined units like molality into their base units so that the units cross out. So I'm just changing this to moles of solute over kilograms of solvent. The kilograms on top and the kilograms on bottom will cross out, and that will leave us with moles of NH3. At this point, if we were making this in the lab, we would have to figure out how to get 0.195 moles of NH3. With most chemicals, we can just use the grams per mole. However, NH3 comes from a concentrated solution, so we'd have to do more work to figure out exactly how many moles or how much solution to start with.
Okay, so we can use these the other way around too. And if I were in a regular lab section, this is the calculation we do to start off the very first lab. I'm still working on the lab for the online class. But how many grams of NaCl are needed to make an exact concentration of solution? And we probably will have to do this as well, just to demonstrate that we're doing the right concentrations. So go ahead and try and solve this really quick. Find the moles, and once you find the moles, find grams of NaCl. Okay, so first things first, we have to figure out how many moles of NaCl we have. So I am going to cross multiply the 0.5 kilograms times the 0.1 molal. Now you have to remember molal is moles over kilograms, so the kilograms here cross out, and that leaves us with 0.05 moles of NaCl. Since we have the moles, we can use the grams over the moles cross out, and that leaves us with grams of NaCl. So if you wanted to make this very, very specific 0.1 molal solution, we would take 2.93 grams of NaCl and add it exactly to 500 grams of water. So let's take a minute and look at how these concentrations are different. Let's look at the molarity and molality of benzene in an octane solution. Again, we have a solvent volume and a solution volume, so plan accordingly. I will go through these one at a time, molarity first in a few minutes, and then I'll go through the molality.
So let's start with molarity. Now, first of all, we need to find the moles of solute. So to get the molecular weight, I just added up 6 carbons and 6 hydrogens to get 78 grams per mole. Since we have 7.37 grams of benzene, we have about 1/10 or 0.0945 moles of benzene. Now, when we're doing molarity, we're going to put moles over the liters, 0.0945 moles over the volume of the entire solution of 0.156 liters to get 0.606 molar benzene in octane. Now, we don't have to calculate moles again here. And, it's hard to do this in an internet class, but often I will put these two side by side. It's not likely to happen, but if you had a problem with both molarity and molality, it makes sense to just hold on to the number of moles. You don't have to calculate it twice. The big difference here is that we need the mass of the solvent. And so now I have to use the density and the volume to cross multiply to get the mass of, depending on how you rounded, 105.6 or 106 grams of the octane. Now I'm going to take the moles over the kilograms, which would be 0.106 or 0.1056 kilograms, to get a molality of 0.895 benzene in octane.